Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson number 9 on geometric sequences. Before we begin, let me remind you that you can find the worksheet and a homework assignment that go along with this video by clicking on the video's description or by going to our website at www.emathinstruction.com. As well, don't forget about the QR codes. Those allow you with your smartphone or a tablet to scan the code and come right to the video associated with the worksheet. Alright, let's begin. Now, we have to really start with kind of a blast from the past, okay? Exercise 1 says that we have an arithmetic sequence. An arithmetic sequence defined recursively by the following formula. A1 equals 5. A sub n equals a sub n minus 1 plus 3. Find the next three terms of the sequence. Okay, it's been a little while since we've dealt with sequences, and specifically since we've dealt with arithmetic sequences. So before we even jump into this, let me give you a little primer, right? A sequence is a list of numbers. All right, that's a sequence. Okay, there might be some kind of real recognizable pattern in a sequence. Maybe there isn't. An arithmetic sequence is one that constantly, whoops, of course I had to pick the one that we were dealing with here. An arithmetic sequence is one where each term is generated by adding the same amount to the previous term. So we add 5, we add 5, we add 5, we add 5. When we define a sequence recursively, it means that we give a starting value, or possibly values, and then we tell how each element in the list depends on elements that come before it. So, in other words, right, what we're saying here is that we have an arithmetic sequence whose first term is 5, and every other term is the one previous to it plus 3. So watch. A2 is A1 plus 3. So 5 plus 3 gives me 8. A3 is A2 plus 3. 8 plus 3, or 11. A4 is A3 plus 3, which is 11 plus 3, which is 14. All right, so these are my next three terms. A term is just one of the elements in the list. Now, it asks me to find the 20th term, a sub 20, without listing out all the 20 terms. So remember, this is a little bit tricky, right? A1 was 5. But to get A2, we added 3 to the 5 once. To get A3, we did really that 5 plus 3, right? We took that 8 and we added 3 again. In other words, we added 3 twice, right? One more and you'll see it. A4, right, was that 5 plus 3 plus 3 that we then added the 3 to again. So we added 3 3s this time, right? And notice we always add one less 3 than what's known as the index, the place in line. So A20 will be that 5 plus 19 3s. 19, not 20 of them, but 19. So that gives me the 20th term as 62. It's very tricky because, you know, it's natural to say, oh, the 20th term. Sure, I'll take the first term and I'll add 23s to it. But that doesn't work. We always add one less than the term because we don't add a 3 to get that first term. Okay? So that's an arithmetic sequence, but that's not what we're doing today. Today, we're looking at geometric sequences. So pause the video now and really process this, because then all of a sudden we're going to jump into the geometric sequence. Okay, I'm clearing it out. So let's figure out what a geometric sequence is. An arithmetic is one where you add the same amount each time to get to the next term. Geometric sequences, you multiply by the same amount. So here's the technical definition. Given the first term, got to be given the first term, each successive term, meaning the next term, successive just means the next, each next term can be found by taking, each term can be taken by, sorry, I can't talk, by taking the previous term and multiplying by a common ratio. Common ratio, all right? So unlike arithmetic, where you add the same amount each time to get to the next term, geometric, you're going to multiply the previous term by some ratio to get to the next one, okay? That may not have been my most articulate expression, but we're gonna see a bunch of examples in the next problem, and that'll clarify. So sorry if I kind of botched that a bit. Anyhow, I'm gonna clear this out, and let's take a look. Exercise 2. For each of the following geometric sequences, identify the common ratio, r, and give the next two terms. That should say ratio, not ration. That's just weird. So what do we have? Well, to go from 2 to 6, we multiply by 3. To go from 6 to 18, we multiply by 3. So the common ratio is 3. To get the next two terms, we're going to multiply by 3 again, and that's going to give us 54. And then we're going to multiply by 3 again, and that's going to give us 162. Now that one's pretty easy because it's pretty obvious that you do 2 times 3 to get 6, and you do 6 times 3 to get 18. But if you're ever curious about what that r is, the way to find it is to always divide two successive terms. So if I do 6 divided by 2, I'd get 3. Or if I do 18 divided by 6, I'd get 3, right? That's the way you can always find that ratio. So for instance, in this problem, right, if I want to figure out what I have to multiply by, if it's not obvious, I would do negative 20 divided by 4, and that would give me the common ratio as negative 5. Now you can check it, right? You can check it a couple different ways. Well, if I multiply negative 20 by negative 5, will I get positive 100? And I do, right? If I do negative 20 times negative 5, I get a positive 100. So then if I multiply 100 by negative 5, I'll get negative 500. And if I multiply negative 500 by negative 5, I'll get positive 2,500. Now, these get particularly difficult when the geometric sequence is decreasing, right, in absolute value terms, decreasing. So take a look at this one. You might think, oh, the common ratio is 2, because I gotta multiply 8 by 2 to get 16 and 4 by 2 to get 8. But we're always going in this direction. So in this case, you definitely want to do 8 divided by 16, and you find that that common ratio is 1/2, not 2, right? If you do 4 divided by 8, that's also 1/2. So in this case, our common ratio is 1/2. We keep multiplying, I don't have a lot of space here, by 1/2. Multiply by 1/2 and we get 2. Multiply by 1/2 and we get 1, right? So that's a geometric sequence. Very similar to arithmetic, very similar. The big difference is that we multiply each time. This should sound very familiar. It should sound like the difference between a linear function and an exponential function. And it really, really, truly is. All right? So we're going to get some more work with this. Pause the video now, write down anything you need to, and then we'll move on. All right, let's do it. All clear? Next exercise. So what we definitely want to do is keep working with both function notation and sequence notation. So take a look at this. Consider the geometric sequence given by this and this. All right, let's just make sure that you can interpret the rule. Right, this thing really just tells me that the first term is 3, right? When the input to a sequence is the term number. So the first term is 3. All right, and then what this tells me is that each term can be found by taking the previous term and multiplying by 2, doubling, right? So B2 is B1 times 2, which is 3 times 2, which is 6. B3 is B2 times 2, which is 6 times 2, which is 12. B4 is B3 times 2, which is 12, times 2, which is 24. Now, letter B says, based on A, determine the value of B of 10 and B of 20. This is really important because what we want to do is do the same thing we did with the arithmetic. We want to figure out a formula for doing this that doesn't force us to go through them all, right? So let's take a look. B2 is our starting value times 2 once, right? We multiplied by 2 once. But B3 is that 6 times 2, which is 3 times 2 times 2. So it's 3 times 2 twice. B4 will be 3 times 2 times 2, that was our previous one, times 2 again, or 3 times 2 cubed. Does this feel familiar? It should feel like two things. That arithmetic process that we went through, but it should also feel like how we modeled using exponential functions, with one key difference, right? The key difference being that this exponent is always one less than the term number, right? So for the third one, we take our starting value and we multiply by 2 twice. To get to our fourth value, we take our starting value and multiply by 2 3 times. So to get our 10th value, we'll do 3 and we'll multiply by 2 9 times. 9 times, not 10 times, and it's huge. It's 1,536. Of course, that's nothing compared to B20. Our 20th term, we get to multiply our first term by 2 19 times, right? And that's quite large. 1,572,864. So there's a big difference between exponential functions and geometric sequences. You know, in exponential functions, pretty much the input is the number of times you're multiplying. But in geometric sequences, the number of times you're multiplying is always one less than where you're standing in line. If I needed to figure out the 100th term, I would only get to multiply by 2 99 times. And that is a little bit tricky, no doubt. But if you write out these patterns, you will see it. Always write out calculations so that you can see the patterns, okay? So I'm going to ask you to pause the video again. Think about this carefully, especially letter B. Write down anything you need to, and then we're going to move on. Okay, let's do it. So let's take a look at the next problem. This is a classic. Everybody that does exponential work or geometric sequence works needs to see this. You have just won a very strange lottery. The lottery promises to give you money each day for a 30-day month based on one of two options, and you get to pick. Option 1, you can receive $1,000 on the first day, $2,000 on the second day, $3,000 on the third, in this arithmetic sequence. Or you can receive $0.01, so 1 penny on the first day, $0.0 or 2 pennies on the second day, $0.04 on the third, $0.08 on the fourth, etc. in this geometric sequence. The question is this simple. which would result in the largest payoff, or maybe the larger payoff, on the 30th day only. I don't care about 1 through 29, just 30th. Show work that supports your answer. All right? This is kind of cool because intuitively, it seems like we should go with option 1, right? Because option 1 is simple. It's an arithmetic sequence, right? What do we know? We know sort of our first term is 1,000, and then our 30th term is going to be that 1,000 plus 29, not 30, additional thousands. Although, no great surprise, that gives us $30,000 on the 30th day. It makes sense. I mean, we're getting 1,000 on the first day, 2,000 on the second, 3,000 on the third, etc. So we're going to get 30,000 on the 30th day. Now, that's a great deal. I'll take that any day, or at least any day that I'm not given option 2. Because look at this. In this case, on our first day, we're given 0.01, right? And on our 30th day, we're going to be given 0.01 times 2 to the 29th. The question is, what does that equal? All right. If you haven't already done this, pause the video right now and enter that into your calculator. All right. That's a big number. I mean, that's a number big enough that for me, I have to write it all the way down and then think about where I put my commas. So if I look at my calculator readout, it looks like this: 5368709.12, comma, comma, holy cow. Look at that. We're making over five, let me really write that out, over $5 million in this case. $5 million on the 30th day. And the day before, we got half of that. We got over $2 million. The previous day, about $1 million. The day before that, I mean, we made a lot of money. Okay? So this goes to show that just generally what we saw in the last lesson, actually, when we compared linear functions to exponential functions, exponentials catch up to linears. It doesn't matter how big the slope is. Exponentials catch up to linears as long as they're both growing. Okay? So pause the video now, write down anything you need to, and then I'm going to clear this out. All right, here it goes. All right, last problem. So in the last problem is very, very easy. I just want to plot a geometric sequence, that's all, because I want to remind you of something that's very, very important about the plots of geometric sequences. So it says for the geometric sequence defined by a sub 1 equals 16 and a sub n equals a sub n minus 1 times 1/2, list and plot the first 6 terms on the grid below. Well, I gave you the first one, a sub 1 is 16, all right? So a sub 2 will be a sub 1 times 1/2. So that'll be 16 times 1/2, which is 8. A sub 3 will be a sub 2 times 1/2, which will be 8 times 1/2, which is 4. A sub 4 will be a sub 3 times 1/2, which is 4 times 1/2, which is 2. How many do I have to do? 6 terms. A sub 5, a sub 4, who designed this worksheet? Times 1/2, that's going to be 2 times 1/2, which is 1. And then finally, a sub 6 is going to be a sub 5 times 1/2, which is 1 times 1/2, which is 1/2. All right, so when n is 1, we're at 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're all the way at the top. A2, we're at 8. 1, 2, 3, 4, 5, 6, 7, 8. Whoops. At 3, we're at 4. 1, 2, 3, 4. At 4, we're at 2. At 5, we're at 1. And at 6, we're at 1/2. And we do not now connect those with a straight curve. So do not connect. Do not connect. All right. It would be tempting to draw a line through it, or a curve through it. But we shouldn't do that. The domain of sequences is simply the numbers 1, 2, 3, 4, 5, 6, etc. Sequences do not have fractional inputs. The inputs are simply the place in line we are. So the first place in line, the second place in line, the third place, etc. So do not connect. All right. Pause the video now if you need to, copy down anything you have to, and then we'll finish up the lesson. All right, let's do it. Let's clear this out and finish up. So in this lesson, we reviewed arithmetic sequences, i.e. lists of numbers that change by just constantly adding the same amount each time. And we used that to introduce geometric sequences, which are very similar, except to get from one place in line to the next place, you're always multiplying by the same amount, known as the common ratio. That ratio can always be found by dividing two successive terms, two terms, one right after another. All right, and then you can use those to predict what you have the 30th term, the 50th term, etc., by always multiplying by one less, or multiplying one less time than the number of terms. Okay. For now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.